So, welcome everybody to today's Heidelberg Joint Astronomy Colloquium. It's our pleasure and honor to have Steve Balbus here as our guest and speaker. I guess for most of you I don't have to introduce him. So he's of course very well known for his work on the magnetorotational instability in accretion disks. And this is often called the Balbus-Hawley instability. And this is of course one of the driving forces of accretion throughout the universe, and therefore it's a big thing that he discovered. He did his PhD at the University of California, Berkeley, and then moved on for postdoctoral appointments at MIT and Princeton, and then in 1985 he joined the University of Virginia Department of Astronomy, and then in 2004 he moved to the École de Maths Supérieure as a professor des universités. And then in 2012, 3 years ago, he moved to Oxford as became the civilian chair of astronomy at Oxford. So today he will talk about another topic, and that is the internal workings of stars, especially the sun, and rotation and convection. And so we're of course very happy to have you here. Let's welcome Steve to Heidelberg.
Thank you, Keith. Nice introduction. So I'm going to talk today about a topic that I've been working on for the past several years, which is, I think, extremely interesting for several reasons. When I was starting out as a student, I think stars were considered kind of passé, boring. We had learned pretty much all that we could from stars, which was quite a lot. But the really exciting stuff was quasars and extragalactic and whatever Martin Rees was working on. That's what people would be working on. But recently, by recently I mean sort of toward the end of the century, late 1990s, we started to gather just a remarkable collection of data from helioseismology, looking at normal modes of the sun, which has enabled us to deduce a huge amount about what's going on in the sun's interior. And that's fascinating in and of itself, and it is a way for us to learn, as we'll see, not just about the sun, but perhaps about what's going on in other stars as well. So I would say one of the most beautiful astronomical results of the last half century has been the precision determination of the interior rotation profile of the sun. And a lot of things happened in the last half century in astronomy, so that's a pretty extreme claim, but I would stand by it. So what is going on in the sun and what we know about it represents perhaps the only non-trivial fluid velocity field in astrophysics that we know with certainty. At one point on the slide, I had to state that it was the only fluid velocity field in astrophysics that we know with certainty. And then someone in the audience put their hand up and said, what about Hubble flow? Well, except for B proportional to R. This is, you'll see, a little more interesting. So this is an interesting test of the state of our knowledge of astrophysical gas dynamics. How well can we do with this? To set the stage, basically, what was thought at first to be just sort of random flickering noise when people observed the sun turned out to be observations of a superposition of lots of normal modes of oscillation oscillations called P modes. P there stands for pressure. These are essentially acoustical oscillations of the sun as a global body. And every internal structural model for the sun, a little bit like an atomic element, has its own spectrum of acoustical modes. So by measuring what modes are present, their intensities, one can invert that problem and deduce what kind of interior structure gave rise to these modes. In addition, by looking at e to the I m5 behavior, non-axis symmetric structure, and looking at how there are slight different frequencies, like a little bit like a Stark effect or a Zeeman effect, this frequency splitting, it's possible to deduce not only the internal structure of the sun, but something that doesn't contribute particularly strongly to the structural profile, namely its rather mild internal rotation. But it's possible to deduce omega as a function of r and theta. My notation here is omega is the angular velocity, rotation rate. R and theta are standard spherical coordinates, r radius, theta co-latitude, measured down from the z-axis, the rotation axis. So by using rather sophisticated inversion techniques applied to the spectrum of these eigenmodes, you could deduce in remarkable detail what the internal state of the sun was, including its rotation profile. What was found, somewhat surprisingly, is that there is significant differential rotation in the convective zone and in a small section even of the radiative zone, the upper layers of the radiative zone. This is strongly, though not exclusively, associated with turbulence, that is to say, regions of differential rotation and the regions where we think the sun is turbulent coincide. Evidently, the turbulence does not erase the differential rotation as you might naively expect. If anything, it seems to be the opposite. It seems to be a cause thereof. And the angular velocity, the angular rotation rate, is found to be roughly constant on cones of constant theta at mid-latitudes, more symmetrical near the equator of the pole. So let me flash on exactly what that means. There is a slice, a meridional slice of the sun taken from the GONG data, Global Oscillation Network Group, I think is what it stands for. And what you're looking at are contours of constant angular velocity. And you're looking at perhaps a change of 25% or so from the poles down to the equator. The sun rotates about once a month at mid-latitudes, and there's plus or minus 12, 15% on either side of that. We identify this kind of characteristic pattern, this bulk of parallel lines. The lines of, that's what we mean by cones. If you take this and you imagine rotating it about the z-axis, the rotation axis, then those straight lines become cones. And that's perhaps the most striking feature of the sun if you just sort of look at it quickly. That requires some kind of an explanation. There's the so-called tachocline, which is a boundary layer between the convective zone and the interradiative zone, where you notice there's a great change in the form of the rotation profile as we try and match up to the radiative interior of the sun, which is rotating more or less at constant or uniform velocity. And then a near surface shear layer, about which I won't say very much in this talk. So here's the problem. The convective zone is very nearly adiabatic because that's what convection does. Convection mixes entropy extremely well. So in the region where entropy is mixed. It's really a constant. That being so, P would be a function of rho only. We would have a so-called barotropic equation of state. Now the convective motions, except for this near surface shear layer, are typically very small, measured in units of tens of meters per second. Now, a barotropic fluid in hydrostatic equilibrium can be shown must rotate on cylinders. That is, omega must be a function of capital R, uppercase R, a cylindrical R, measured from the rotation axis. So I offer what I call a Bhaskaran proof. Anybody in the audience? You'll see how well we're educated in our youth these days. Anybody know who Bhaskara was? Bhaskara was an Indian mathematician of the 12th century. And he's famous in mathematical circles for a one-word proof of the Pythagorean theorem, which I reproduce in its entirety in this diagram here. And so I'm going to offer a one-line proof of this last statement that a barotropic fluid in hydrostatic equilibrium must rotate on cylinders. Namely, I simply write down the equation of motion. So here's my centrifugal term, r omega squared, in the r direction, or this is, remember, cylindrical r. Here's my gravitational potential plus 1 over rho grad p. In the case when p is a function of rho, then the entire right-hand side is a gradient itself, called gradient of upsilon. And then I note that since the gradient of upsilon has only a component in the radial direction, upsilon itself can depend only on capital R. And if upsilon depends upon capital R, then omega can only depend on capital R. So it's a very simple and powerful result that applies to barotropic fluids. The problem is that in the convective sun, the solar rotation profile is decidedly not constant on cylinders. It is not barotropic, it is somehow baroclinic. And there's a big difference between the two. So let's look at this in a little bit more detail. If we look at the equation of vorticity conservation, so I think this is a physics department, I'm not going to make excuses for putting up some equations. I will try to make it not too onerous a task to follow me. But if I write down the equation of motion, so there's the v dot grad v term in the Euler equation, and set that equal to grad p over rho minus the gradient of phi. Phi, once again, is the gravitational potential. P is the pressure, and rho is the mass density. And then I rewrite this v dot grad v term using a vector identity as the gradient of v squared over 2 plus omega cross v, where omega is the curl of v, that's the vorticity. And then I take the curl of the whole thing. I get an equation which looks like what you see in front of me. The curl of v cross omega is grad p cross grad rho over rho squared. That's the equation of vorticity conservation. And you can see immediately that if p is a function of rho only, the right side disappears identically, and we have a statement of a conserved quantity, or at least that this v cross grad omega is derived from the gradient. And I'm interested in the phi component of that vector equation. Now, what people like to do in the study of the sun, and actually more generally, people do this in geophysical applications as well, is to derive something called the thermal wind equation, which is particularly useful when you have rotation in a very nearly adiabatic background. So I start with the vorticity equation, and I stick in that my velocity field is going to be purely rotational. So it's r times omega, and then e phi, those are always my unit vectors, phi direction. And then then if I go through the sort of manipulations that you see, the left side, when you work through that combination of double cross products, turns out to involve only one term in this case, which is the z gradient of omega squared. So you can see now why having something that depends on the vertical direction is important. It comprises the entire left side of that equation, the vorticity equation. When I have a pure rotation profile, I take one of the rows and I stick it inside the grad row, so that gives me a logarithmic derivative. And then I do a cheat. Inside this logarithmic gradient, I'm sticking in a p to the power minus 1 over gamma. Gamma is the adiabatic index. For purposes here, it's 5/3. So what have I done there? Well, I'm headed someplace, but you can see it doesn't make any difference because the error that I incur by doing this is proportional to grad p cross grad p, and that's 0. Nevertheless, once that's inside this logarithm, I take out this minus 1 over gamma factor, write it as p rho to the minus gamma, and now I have something which involves the entropy only. And that's useful here because the entropy is a tightly controlled quantity inside a convective zone, which is why people like to write the equation in this particular form. And then the dominant term here for the gradient of p, since the rotation for the sun doesn't cause any significant dynamical distortion, the centrifugal force of the sun's rotation is a tiny, tiny term. Essentially, the gradient of p can be replaced by its radial component, and the minus 1 over rho grad p becomes proportional to the gravitational field, and I get a very elegant looking equation at the end. So this is the gravitational field, and in the portion of the sun I'm interested in, all the mass is pretty much below the convective zone. So it's simply Gm over r squared, it's Newtonian gravity, m being the mass inside, or the bulk mass of the sun. Sigma, you remember, was the quantity, my entropy variable, the log p rho to the minus gamma, and theta is the spherical coordinate theta. So this is a neat looking equation. It relates quite generally in an adiabatic zone the z gradient of the rotation to the latitudinal gradient of the entropy. Evidently, it predicts that the sun should have some kind of a dependence of theta, and the entropy should change, and what that means practically is that the temperature should change from poles to equator. Large-scale latitudinal entropy gradients cause departures from cylindrical isorotation contours. And then the trend in the sun is that as we move polewards, omega decreases, and therefore sigma increases. The sun should be a little bit hotter at the poles than the equator. This has been measured, and indeed it is. And it's actually rather amazing because it amounts to simply a few degrees out of a million degrees, which is the characteristic temperature of the convective zone just underneath the surface. To orient ourselves, what are we talking about here? If I write this equation in a dimensionless form, the gradient of omega squared is a 10% effect. I've divided through by omega squared. Here I have the ratio of the gravitational term to the centrifugal term. That's enormous. That's a factor of 100,000. So we infer you couldn't possibly measure this, or you could just barely measure this. I just sort of contradicted myself. They actually do have some kind of measurements now. So that's a part in 10 to the 6. So these are tiny effects that we're talking about. By comparison, the radial gradient of the entropy, you need to have some kind of an adverse radial entropy gradient in a convective zone. That's why it is convectively unstable. It's a classic result going back to Carl Schwarzschild. When the entropy decreases outward, that is what triggers convection. But that's a factor of 20 or so larger in the radial direction than it is in the theta direction. And the radial entropy gradient by rate, which is this quantity here compared with omega squared, if I write it in a form where both of these have units of 1/2 squared, in the convective zone, these two things are comparable. So the point is that there's a small number in this problem, which is the ratio of rotation to gravity, same order as the rotation velocity to the sound speed, a number of about 10 to the minus 5. It's a centrifugal parameter. It's important to keep that in mind when you think about the sun. It's a very small parameter here that can pop up in interesting ways. In particular, if I go back and I write the thermal wind equation in this form, you may remember before I did it in terms of the entropy, if I do it in terms of the temperature, what it says, if I'm doing a simulation and I want to try to reproduce just by brute force what the internal rotation of the sun is doing, there's a 1/epsilon that appears here. So unless I have the isothermal surfaces and the isobaric surfaces correct to 1 part in 10 to the 5, the answer I get will be worthless. You will not be surprised to know or to learn that when people do try and do the simulation, it washes out and they find that d omega dz is equal to something like 0. And so the simulations reproduce rotation on cylinders. And I think that's not an accident. So, our task is to solve this equation. The theorists would solve equations. Now, one small little problem. How do you solve one partial differential equation with 2 unknowns? Anybody can solve a well-posed. It's a good theorist to solve an ill-posed equation. How do you do that? Well, you have to know something about how sigma and omega are related. Let us begin with the basics. This is a convective zone. If psi is my radial displacement, here is my equation of motion. This basically, within linear theory, I'm growing exponentially at a rate given by this combination of terms. This is the gravity adiabatic index 5/3. My entropy gradient is n squared. This equation defines is called the Brunt-Weisel frequency. Now, n squared will be negative in a convective zone because it's unstable, but in the radiative zone, n squared will be a positive quantity, and so displacements oscillate up and down at this very characteristic frequency. Now, within the sun's convective zone, what are the basics? What's the basic physical process of convection doing? It's carrying the heat flux out from the sun, and it has become convective because the outer layers are, in some sense, too cool relative to the interior. The most effective way to get the heat out is to lift it up mechanically, have a radiative surface, and the cool blob cycles back down, and the process of convection takes over the radiative transport. Now you can show that the net heat flux that you get is proportional to a very high power, n cubed, of the entropy gradient, and therefore it's very, very tightly constrained. It has to carry exactly 1 solar luminosity through the sun's surface. The sun's been there for 4.5 billion years. By now found a happy equilibrium. the radial entropy gradient itself can't vary very much from one convective cell to another convective cell. Remember, these things are predominantly, overwhelmingly in the radial direction. The entropy gradient in the radial direction is very tightly constrained. What about the entropy itself? There's no particular constraint on that. The entropy, that is to say the offset relative to the gradient, can vary from one convective cell to another, as long as the convective cells are mixing across one another. That's how you define this stuff. So that's very interesting from a mathematical point of view. If I write down the entropy, then it's some function of R. This is the big piece of it, plus another function of R, which I expand in that series of powers of cosine theta. Then the first term has a strong R dependence and it's very tightly constrained. That's what sets the radial, purely radial gradient. The second part of it has a relatively weak R dependence, because that's the part that's been mixed throughout the cell. So the sigma 0 is what drives the background, and then the sigma n are essentially constants. There's a weak R dependence, there's a theta dependence, because the entropy can differ from latitude to latitude. In fact, we know that must be going on in the sun, because the thermal wind equation tells us that there is a non-zero theta gradient. It doesn't have to be very big. If I subtract off sigma 0, and just look at this part, I'm going to give this a name, it's delta sigma. That's the residual entropy, delta sigma, and this is a very important function. The stuff you don't care about turns out to be what you should care about here. It'll prove key to the analysis. So I've taken the dominant radial, or how shall I say, radial dependence of the entropy, which is responsible for driving the convection, subtract that off, and I have something which is mostly dependent upon theta. Interestingly, when people do numerical simulations, what they actually calculate, because of this difference between the part of the entropy that depends on angle and the background driving entropy, which is big, they put this part in by hand. They put the driving entropy, that's a given function, and then they let the sun respond to that. So what they actually calculate is delta sigma, the residual entropy. It's very, very close to what they actually calculate. Delta sigma is the response, and it's swept clean of variation. Because that's what convection does. It gets rid of the entropy gradient beyond a certain point, beyond what you need to carry that one solar luminosity out. That's the convective process itself. There's a much greater latitudinal cell-to-cell variation than there is within a cell. Let's talk about some heuristics now. The thermal wind has what physicists would call a gauge invariance. That's a rather fancy way of saying something kind of obvious, which is that I can add any function to R there and that will not change the equation. So in other words, in the thermal wind equation in particular, I can write it in terms of delta sigma. I can subtract off that sigma 0 of R and work only with the residual entropy, the stuff that actually varies with theta from one convective cell to the other. So I'm interested now, when I want to solve this problem, not so much in finding a relationship between the rotation omega and the entropy itself, but only that piece of the entropy, the residual entropy. Where am I going? Well, evidently, just like the entropy, omega, there's the data, and obviously omega is a relatively weak function of R. Here's the gradient, just like delta sigma. You're looking at the contours. This is what the best simulations have produced. This is now quite a while, almost 10 years ago. This is a plot of the pattern of omega, the angular velocity, delta sigma. The colors are different because they have actually opposite signs. One is increasing, the other is decreasing. But if you look at the shapes of the colors, in particular the shapes of the contours, you notice there's a remarkable correlation, and there's absolutely no correlation whatsoever with the entropy itself. This is interesting. Both omega and delta sigma, not the entropy, delta sigma, they're both weakly R dependent. I pose the following, what's the good word? Ansatz. It's the ansatz. What if omega and delta sigma in fact share isosurfaces in common? Which evidently they do. If delta sigma is some function, which I haven't specified yet, of omega squared, that's the same thing as saying they share isosurfaces in common. Then TWA, the thermal wind equation, the characteristics of that partial differential equation. All know what characteristics of partial differential equation. With me on that? They would define isorotational surfaces. Here's my equation. My equation is telling me that omega vanishes on some curves, I guess in this particular formulation, in the z theta plane. We'll quickly go over to a fully self-consistent set of spherical coordinates. Now the function f prime, which I write for the derivative of delta sigma, that's not known a priori. But it's okay. So here's the full thermal wind equation with the ansatz that delta sigma is a function of omega squared, written in r theta. So this is at first a little bit scary looking. F prime, remember, is a function only of omega squared. How do we solve this equation? This equation says that omega squared is constant along the characteristic d theta dr equals this stuff. Now, I don't know what this function f prime of omega squared is, but it's a function only of omega squared, and omega squared is by definition a constant along the surface I'm calculating. So f prime, for purposes of solving that ordinary differential equation, is simply a constant, which is good. This equation looks a little scary, but in fact, it's the only time in my research where something has turned into a textbook problem. He simply said y equal to sine theta, and this reduces then to a first order linear ordinary differential equation, the kind that you learned when you were still in diapers. Here's the solution. R squared sine squared theta, which is in fact the cylindrical coordinate r, is simply a linear function of 1 over r. 1 over r is the gravitational potential. And that's not an accident. You can solve that equation more generally. What you get is not minus 1 over r, but 5. For our purposes, keep it simple. B is this particular combination of terms. Newton's G, the mass of the sun, F prime, which is a entropy gradient over O, so it has units of entropy over omega squared, gamma simply 5/3. The crude estimate is that this is a number in dimensionless form. V over the cube of a solar radius is a number less than, but of order 1, which is nice. And the basic result of this solution is pretty clear, isn't it? It said when I'm near the axis, when capital R is small, the dominant balances these two terms so that R is a constant. When I am far away from the axis, like at the equator, then the dominant balance is between these two terms. So that cylindrical R is a constant. And that indeed is exactly the trend that the data show. More specifically, what we would do to construct a solution is to begin at some surface. When you solve a partial differential equation, you need to specify the data on the surface, and then the characteristics tell you how it propagates off that surface. So the basic form of this curve is I begin at some point R0. I write beta as a dimensionless constant, which thus far is simply a free parameter in theory. But there is the mathematical form of what the helioseismology data should be doing. In other words, in this view, the helioseismology data is like a giant analog computer. It has solved the thermal wind equation for me, and it is displaying the solutions in the form of the isorotation contours. How good is the fit? Well, when I was in Paris, I had a German student, Julius Bonard-Cohen. My feeling is if you want mechanical drawings done precisely, these are the kinds of students that you need to work with. So Julius came in and in a very stoic sort of way said, I think this looks pretty good. That's what we came up with. And just to remind you, we're only interested in the convective zone, not in the tangent line. So focus on this region. And there is the fit. I mean, I don't think there's much doubt. That can't be an accident. And even if you don't bother fitting, you just say, I'm not going to beta couldn't principle that vary from one curve to the other. If I just take a global value for beta, this is the kind of result that you get, and certainly the qualitative constant, or the qualitative content, is still there. That's a one-parameter fit to the entire sun. So there's something right about the theory. We need to understand it a little bit better. Why is it that the residual entropy and omega care about each other? So I've explained, I think, physically why it makes sense that entropy should be more or less constant along a convective cell, but could vary from one cell to the other. But what is it about the angular velocity that also makes it want to be in this kind of a configuration? Well, a Taylor series expansion for delta omega squared of R. I can always write the entropy equation. Normally you write it in terms of R and theta. Let me write it in terms of R and omega squared. So this will be a function of omega squared only. R0 will be the midpoint of the convective zone. And then the first order correction is R minus R0 delta sigma over R. Well, you can see what's going on. The physical basis is that this gradient, we've already said, is going to be small. R minus R0, the convective zone is only 0.3 solar radii. If I'm in the middle and I go from one side, that's only a variation of 0.1 R. So I have a quadratic correction to this, just simply by a straight mathematical argument alone. So it's not surprising that this works as well as it does. It's inevitable. It's more a test of the thermal wind equation itself rather than a test of the physics of the relationship between entropy and angular velocity. Convective cells live in, they maintain constant delta sigma surfaces, but we can also show now in a little more detail why coherent, long-lived structures live in surfaces of constant omega as well. View the mathematics, it's a little more involved, but I think you can see the idea. If I go into coordinates which are actually shearing with the background flow, then what I find is when I express my gradients in terms of these Lagrangian coordinates, which are tied into the shearing background, they acquire this dependence of time. Essentially, this is what how my gradients transform, and my wave numbers as well. Wave numbers embedded in the fluid get sheared around with the velocity gradients. And if I see what does this actually do for something as simple as mass conservation, if I expand the mass conservation as a simple Fourier expansion. There's nothing linear about this. This is just expanding the mass flux as a Fourier series. Bearing in mind that my K is now time dependent in this way. And I impose the condition that divergence of rho v equals 0. Then if Kr is relatively small, if the initial K, colloidal K is initially small, I'm dominated by this term. And there's actually a very good reason why that should be the case, which I'll come to momentarily. But you notice, in that case, K is dominated by a piece which is proportional to the gradient of just a kinematic effect, gradient of omega. So the statement that the divergence of rho v is 0 is simply a statement that K times each component of the mass flux is individually 0, which means that the gradient of omega dotted with the component of the mass flux is equal to 0, which means that essentially the mass is moving along surfaces of constant omega. Why should the initial K0 be small? That's because that's fastest growing mode in convection. Getting ahead of myself. If the same convective rolls live in surfaces of constant delta sigma, and they live in surfaces of constant omega, then obviously they're the same surfaces. So this is what I want to close. Why is it nearly 0? These are the fastest growing modes. The fastest growing modes in the sun, interestingly enough, was shown. This is one of these classical results whose content has sort of been lost. Shown in 1951 by Cowan that, in fact, rotation makes no difference to the nature of the fastest growing convective modes, unless you're rotating very fast. For something like a star, it makes no difference whatsoever, which sounds bizarre, because this is stuff moving radially outward in the absence of rotation. That's the way the heat's going. And if I rotate, there are Coriolis forces. Why don't the Coriolis forces have an effect? There's a rather scary-looking dispersion relation for a general disturbance of omega as a function of wave number k. I have a bunch of crazy-looking derivatives. The fastest growing mode is one where this term is absent at all. There's no kz, and I have a pure e to the I m5 disturbance. Everything is entirely azimuthal. That gives me an omega squared with this coefficient of unity, and then I get back to my Grund-Weisel frequency, this rapidly growing mode. There's no Coriolis effect for the most rapidly growing mode, and the reason for that is geostrophic balances, it's called. In essence, the Coriolis term is exactly canceled out by an azimuthal pressure gradient. situation, actually, that we have disturbances in the atmosphere on the Earth. So, all of this starts to make good physical sense. In fact, if I actually look at what the displacements of a convectively unstable system look like, this psi is the displacement. There's the actual equation of motion. It has a Coriolis term, it has a gradient of omega squared, and it has a gradient of entropy. Notice psi dot rad omega squared and psi dot rad sigma. The entropy and the angular velocity are already coming in on the same footing in the basic dynamics. If I take that full set of equations, what I find, if I look at the effect of a small amount of differential rotation, the radial component is growing exponentially, like we saw before. The theta component has a poleward deflection. D omega squared dz is negative in the sun. And I find that I'm not precisely radially outward, but my contours are shifted a little bit up toward the poles, which is why the poles are hotter. And also, if you actually look at the contours, they are in fact not exactly radial, they're slightly shifted up. Even that level is already contained in this rather simple linear theory. So this picture all makes sense. Here's a cartoon. In a constant omega surface, I have convective cells happily moving along. They do not conserve their angular momentum. Get that, picture that in your mind. Don't conserve angular momentum here. The cells that are set up, and the pressure gradients that are set up, exert torques to keep things moving in constant angular velocity surfaces. That's a very important feature of the sun. To summarize, part one, entropy is most efficiently mixed in surfaces in which the convective cells are not shear, constant angular velocity sheets. You know, when I put it that way, perhaps it's not too surprising. When I implement this mathematically, delta sigma is a function of omega squared, it actually turns out to be a very powerful analytic tool. And I can deduce the form of the isorotation contours just directly by solving a partial differential equation, which says that vorticity is, if not, I shouldn't say conserved because there is a source, but vorticity, how shall I put it, requires a source, rad p cross rad rho. Just a direct solution of that equation. It's the old-fashioned method, pencil, paper, and equation. What about the tachycline? Well, I'll have to zip through that. That's actually difficult to understand in detail, but it's possible to do something. Let me give you an idea of what's going on. And let me give a full disclosure at this point. You notice that one of the solutions could have been that omega is constant on cylinders. That would be okay, and in which case sigma would not be a function of theta. That is a solution. It's not the solution that the sun picks. And so a more profound question is what is actually forcing the sun to get away from rotation on cylinders? And I think the answer lies in the tachycline itself. You can sort of see what's going on. There's something very different about this region here when I join on to this boundary condition. Without convection on a perfect uniform rotation, I need to join on to that in some ways. If I look at the fundamental thermal energy, not energy equation, I should be careful, entropy equation, basically second law of thermodynamics. It says that d sigma dt, sigma, remember, is just my entropy variable, log v rho minus gamma, plus v dot grad sigma, and here is the radiative flux. If I have uniform rotation, say, then it's very simple to show that the pressure, the density, and the equipotential surfaces all share the same spherically distorted isosurface. The sun scrunches a little bit this way, it bulges a little bit this way, and the pressure, the gravity, the density, the temperature are all constant on the same surfaces. Now, if I look at the entropy equation in a time-steady system, the sun is 4.5 billion years old, one of the things that you'll read in Martin Schwarzschild's book is that when I have a rotational distortion and everything is stratified on the same surface, I can't have radiative equilibrium. The divergence of F must vanish. Things are too far apart of the equation to scrunch down the poles. That can be made mathematically precise. Well, here's the problem. There is a part of the sun where the gradient of sigma does vanish. Right? The sun has a radiative convective boundary. That's the start of all this. And it's precisely in that region. There aren't any terms I dropped from this equation, except the time-dependent one. So if this is vanishing, how can this not vanish? Well, the answer is that the sun is not stupid. The sun knows that it can't be in a state of uniform rotation, nor can it be in a state of barotropic rotation, which also would suffer from the same problem. The sun must get into a baroclinic state somehow. And so that is what it does. That's what forces this departure from rotation on cylinders in the bulk of the convective zone. Its origins are being forced by the region where the gradient of sigma vanishes, at the outer layer of the radiative zone. This is precisely where the trouble is, and you notice that's exactly the region where there's this abrupt change in the nature of the rotation profile. So here's the thermal wind equation. We've decided in the SCZ, in the solar convective zone, delta sigma is a function only of omega squared, but in the tachycline, we write it as a function of omega squared and theta. Notice the trick here. I don't write things in terms of R and theta. Physics is writing it using omega as my, how shall I put it, my spatial variable. That's what allows all this to go through. So in the absence of vigorous convection, we need to fit the inner boundary condition of uniform rotation. Those of you who do fluids maybe remember the Beckman layers, where if I have, for example, a viscous fluid, in the bulk of the fluid will be rotating on cylinders. Near the end caps, I have a very small region where the nature of the rotation profile changes abruptly. The sun has an analogous situation with its convective zone and its radiative interior. In the convective zone, the thermal wind equation looks like this, with delta sigma a function of omega only. When I get to the region of the tachycline, which is what I'm talking about here, then I have this additional term, the derivative of sigma with respect to theta at constant omega. And that is an equation that I can solve directly as well, provided only that I take the simplest possible deviation from zero for the right side. If I take the entropy to be a very simple polynomial in cosine theta. I don't know this a priori, so I'm cheating a little bit. I just want to see whether the equation is actually describing what is going on. And if you do that, this is what you find. The black is the data. The red is the fit from the convective zone through the tachycline. And that's the form of the fit. Once again, the overlap is such that I think there's no question that this is the fundamental equation which is governing the actual solution of the sun. The precise physical reason for the entropy having the form that it does is something that still needs to be explained more fully. The tachycline is a very complicated region. But the fact that we're in this thermal wind balance, which is the equation I'm solving, given the fit that occurs, there's no question that that's describing the underlying physics of that process. So, the last 5 minutes, and then I will stop. Thank you for being patient with what must be a rather technical talk. Let me pose the question, can we construct a rotation profile in strict radiative equilibrium that agrees with the that's supposed to be helioseismology data? So this was the topic of a thesis of Andrea Caleo, a student of mine. And we went about doing precisely that. We wanted to set up a problem, and we turned the problem backwards. We allowed radiative equilibrium to determine everything, including the correct rotation profile. We did an expansion. There is the gong data. There is our model fit. That's not the solution, that's just the underlying background fit that we did to as our zeroth order approximation. And then we compute the corrections. This is simply a mathematical technique. It's a Larkin expansion. And since I'm short on time, I'm going to pump through there. The difficult part was the actual radiative equilibrium requirement, which is a very, how shall I say, small-looking equation that turned into a very big equation when you actually solve it. And to make a long story short, black is the solution from the gong data. The dotted lines were the solution that we found. The point being that given the uncertainties, which are actually very large, to reproduce what the sun is doing on the basis of a model which demands radiative equilibrium actually works extremely well. Here are the contours from the data, and here are the contours that we find in our best model. It works in this sense. Is it stable? Experts in the audience will worry about something called the Goldreich-Schubert-Fricke instability, which this ought to be subject to. In fact, it's stable to the GSF instability, but there you'll have to invite me back for another lecture if you can stand it, and I can explain why. Let me summarize. Here are the data. Heuristics tell us that omega is primarily a function of theta in the convective zone. If I define a quantity called the residual entropy by subtracting off the background entropy profile, demand that it satisfy the thermal wind equation, and also require that the residual entropy be a function of theta as well. That motivates me to look for solutions in precisely this form. There are mathematical arguments that suggest this. There are physical arguments. Convective cells like to live in constant omega surfaces. That's conservation. Simulations indicate that this is what is going on if you just look at the results, since they actually plot the residual entropy. This can be plugged into an equation that you can actually solve. And then you can also come to the problem the other way and allow radiative equilibrium tackle time and ask what kind of solutions are consistent with that. Every one of these roads leads to the same result. So I think we have a handle on what's going on. A simple theory, you'll notice, simple, well, maybe not if you're sitting there plowing through the equations, but it's not a theory that requires a theory of turbulence, closure relations, and all this other stuff. This is writing down hydrodynamical equations and solving them more or less directly. Where do we go from here? Well, this is a powerful diagnostics. In a convective medium, we know how to relate entropy gradients now to angular velocity gradients. We know how to construct omega as a function of r and theta analytically, possibly for dynamo theories of the convective zone. We would like to know what this function is. My theory does not address that. So this is people who like to do mean field turbulence theory. This is a well-posed problem for them. Can we relate the residual entropy to omega squared with an explicit function? When do we need meridional circulation? That was the classic way to maintain radiative balance. Can't do meridional circulation if you don't have an entropy gradient balance. Something that hasn't been pointed out as far as I know. Fully convective stars can be treated in the same way. Michael Weiss and I have looked at this problem. And finally, we're in an era of extrasolar planet research. There are lots of giant gas planets in the universe. Are these very different in their internal rotation profiles? This is an interesting question that might be able to be approached by the sort of techniques I talked about here. At this point, I better stop. Thank you.
Very much, Steve, for this fascinating talk. So we make a little bit more light. Now we go for questions. As traditionally, we start with questions from students and postdocs. So let's start with questions from students and postdocs. Anyone? Okay. Well, let me run up here and give you the microphone.
So the sun is rotating rather slowly compared to, say, massive stars, what we think at least. And so how applicable is this if you are, say, at 90% of critical rotation or so, which is what some people say from their stellar movements?
So I didn't quite get the question. How would this change if the sun is...
Like you have to make certain approximations and certain terms are small, that might really change if you go very close to the critical rotation when the star is close to breaking up into...
Yes, I wouldn't want to take the theory over that I've given and apply it to a star which is rotating at a level where the centrifugal parameter is starting to approach unity. There you really do start to see differences between the rotating and the non-rotating state. And the sun at one point in its career may have been rotating considerably more rapidly. But I suspect that, although it's not really well understood, that somehow or the other magnetic braking is responsible for the slowdown over time. The basic answer to your question that this is restricted to stars in which rotation is important but not dynamically important is well taken.
Okay. Other students and postdocs, or shall we just open for everybody? Let's open for everybody. Yeah, who?
So you said that convection is actually not modified between in theta angles due to rotation, because you said that Coriolis forces are small. But you were talking about now possible sources for the entropy difference between the equator and North Pole. So you say it's not, but then you say again the weak field theory. So it loops again into the same topic. Isn't it in the end a modification of convective turbulence due to rotation?
Ultimately, but what's interesting is what modifies it in the case that I've described is the specific baroclinic background. The rotation itself, I have uniform rotation. In fact, that surprisingly has no effect whatsoever on the behavior of the most rapidly growing mode. Which is surprising. And it's not just that the Coriolis forces are small, at some level the Coriolis force are as big as they ever are, but they're exactly balanced by these pressure gradients. But everything then changes when you have a baroclinic turn. Then the convection certainly is modified in the ways that I've described. And so we have kind of a chicken and egg problem. What is it about the sun that requires baroclinic rotation to be present? And my argument is that there's no other way that it can find an equilibrium. It can't do an equilibrium where it's doing meridional circulation at the radiative convective boundary because there's no entropy gradient to work with. So I think that's the origin of where this all starts to, how shall I say, come apart.
You already have it in the outlooks, apparently you already have written the paper, the transition to fully convective star. So just to comment on how to address the problem with the absence of the decocline. So does that mean that the rotation can become barotropic? And if so, does it have to be barotropic?
Yeah.
Will it be?
That's an excellent question. So we have written a paper. It was the paper that was written very early on, which was in 2009 or 2010. And the paper at that point was concerned with presenting what the rotation profiles would look like when instead of having a 1 over r potential, gravitational potential, we use potentials from the Lane-Emden equation. So that was the content of that paper. The question that you asked at some level is a much more interesting one because of the emphasis that I put on the existence of the convective radiative boundary as the reason for the sun's departure from rotation on cylinders. If I have a fully convective star, I can't use it. So I don't know what the answer is, but I think you're right. I think now, if I would go back, I would argue that fully convective stars may indeed show a profile which looks much more close to rotation on cylinders for exactly the reason that you put your finger on.
So you didn't need to calibrate turbulence? Because essentially
No, we finesse, that's the whole, this sort of method finesses that problem.
Sorry?
It's I don't know if that's it gets around that problem. You don't actually need a theory of turbulence. Where do we use turbulence? We use turbulence ultimately in the physical description of saying just a very straightforward statement. The entropy gradient smoothed out within a convective cell up to the gradient that's required for driving it.
Yeah.
And then the understanding that the convection occurs at surfaces of constant omega and constant residual entropy. That's the turbulence theory, as much as it is.
I mean, since you worked essentially with Euler's equation, you did not need to calibrate the turbulent energy flux. So I was wondering, since you now have a very good fit to the internal structure of the sun, you could return this and constrain the amount of turbulent energy flow. For example, you could calibrate the mixing lane theory.
Perhaps what I would argue, I may have not be able to do that, because what I would argue is that where the turbulent energy flux is important is actually in setting up the actual form, the initial condition of the rotation profile. What I haven't really answered is why is omega sort of increasing toward the equator? Nothing I've said directly addresses the problem of why it couldn't have gone the other way. I sort of use this as my initial condition and then I integrate inward. I suspect if I wanted to address the question of why it's set up in this particular way, then I would need to know something about the initial turbulent energy fluxes. I agree with you there, but I don't know that I can constrain them this way directly from the equations themselves.
Okay, are there any further questions? Look around. I actually have one question concerning the last point you made here, the rotation of gas giant planets. I find very fascinating because I've always wondered about the following problem. If you look at Jupiter, it's not rotating not even nearly to at breakout. Yet it has been formed from an increasing disk, presumably at some point, at a certain planetary disk. And I could imagine you need strong magnetic fields from the planets to have magnetic braking on the disk to prevent it from spinning up while it's secreting matter from the planetary disk. And so I could imagine the fact that Jupiter and Saturn are not rotating very fast means at some point in their lives they must have had strong magnetic fields which might relate to this differential rotation going on during the formation phase. Is that something that makes sense to you, or do you think, well, I'm way off?
No, I don't think you're way off. I don't know if you're way on. Because I can imagine a couple of different things, depending upon how important and how overwhelming self-gravity forces are that can form extensive spiral structure in the formation phase. I suspect, though, that you're probably right in that that's not enough. And so what I would expect to see in a case like this would be during the formation phase, where obviously there are a lot of transient and transitory effects going on, is something like magnetic, not magnetic, but MHD turbulence. Let me just call it turbulent transport. At work, getting angular momentum from out of the interior onto the surface would then something like you need some kind of an alpha ultimately, I think, with magnetic braking ultimately to get rid of it. The kinds of processes that I'm working with convection and rotation, will be, I think, at least give you some handle on the sort of transport processes that maybe we're working with here.
Further questions? If not, then let's thank Steve again.